slide I just want to show you that I put up on the Gaucho Space website. Several readings. This is the chapter from that same book on spatial statistics in R that talks about spatial point processes, which will be the first part of today's lecture. And then these next three are about specifically about species distribution modeling. This is kind of an overview. This talks about how implementations in R, and this talks particularly about Maxent, which is one of the most common and most mysterious models that's used for this. So what kind of problems are we working with? It could be if we could be trying to predict how a species range is going to shift under climate change. So we need to develop a model that relates occurrences to environmental variables, including climate variables. We could we might want to develop a predictive model of risk to property using spatial information about past insurance claims. And this is actually a problem that Giuliano has. Or we could have, we might have information on the location of polluting industrial facilities. We want to see whether, to what extent those are associated with areas of low socioeconomic status from a sort of environmental justice perspective. And so in each of these cases, we might imagine that we have information about the location of facilities or location of insurance claims or locations of where we have observed species. And then we also have spatial data on whatever the relevant potential explanatory variables might be. And so that's the problem that we want to tackle. And so it's different from the spatial sampling that we had, or certainly in some of these cases, it's a little bit different from the data we were looking at before when we were doing geostatistics, because although those were data observations at points in space, that's just where we looked, but it wasn't as though zinc only occurred in those places where we looked. Whereas in some of these cases, we're actually going to have information on every occurrence, or what we're saying is this entity occurs here and doesn't occur here, okay, as opposed to what's the concentration here versus the concentration here. So in fact, that's this first case. So if we have locations of all occurrences, often these are called, the occurrences are called events. And so the event or the entity, so the event is the occurrence. The entity, so in this case we assume that the entity is whatever it is we're looking at, whether it's species or industrial facilities or insurance claims, is absent from all other locations. We could have just the location of some occurrences. Okay, and this is often the result of, this is often what we have when we have observations of species. So for example, the CNDDB, the California Natural, someone help me out here, do you know what the CNDDB is? Diversity database, yeah. So it's a database of observations of species, at least species of concern. And it's just a kind of an opportunistic sample. It's all the museum records. It's, when naturalists go out and they see a species somewhere, they report it in. And so there's a location and an observation. That California condors were in this particular location at this particular time. but you don't know, but you don't know, whether it was whether it was another individual present somewhere else, and we don't necessarily know about absence for other locations. Similarly, even if there's a systematic survey that samples the landscape, goes out and takes plots, and records presence from a set of plots. Again, we don't know about presence or absence in other locations. And then we can have true presence-absence data, where at each location where there's a sample, this really is a sampling now, we have a record of whether the entity is present or absent. And we also, we still know nothing about what's going on outside the plots. And if the plots are large, we may have to worry about whether these really represent points. And yeah, so those are typically the kinds of data that we work with. So let's start with this first case, which is we have a location of all occurrences, and there's a branch of I'm not sure whether it's probability theory or statistics or somehow the intersection of the two, called spatial point processes that deals with this. So here's just 3 examples of what a spatial point process could look like. These are maps of some redwood forest, so it's the location of all the redwood trees. This is a map of Japanese maples in a different forest. And this is a map of the nuclei of cells in some tissue. Okay. And so typically we're interested in asking 2 kinds of questions. One is, are there interactions between the individuals here that would lead to their distribution being non-random? And second, if there is sort of spatial pattern in the distribution, can we explain it using either geographically, just by mapping kind of an intensity field, just like we did for concentrations of zinc, or can we explain it using environmental or other variables that we also have maps of? Okay, so when we had the chemical data that we were looking at, right, at each point we actually had a value, right, a continuous value. Here we just have the presence or the absence. And so what we want to infer is something like, what's the probability of finding a tree in this location versus this location? Okay, so it's more like it's like thinking about logistic regression. So what we look at is the intensity function, which is usually denoted lambda. Okay, and it's kind of like a density, right? You can say it's really if you look at a unit area, it's the lambda tells you the expected number of occurrences in that unit area. And the standard model for a random point process, if it is that if a given little box with area A has intensity lambda, then the actual number, so the expected number of occurrences is just lambda, is lambda times A. The actual number of occurrences is going to be a Poisson random number with that parameter. So this is a model of spatial randomness. And then if lambda is constant in space, then we have what's called complete spatial randomness. So that just says that the intensity field is the same everywhere, and we're just putting dots down at random. So equivalently, it would be if the X and Y coordinates, we just drew a bunch of random numbers, uniform random numbers between 0 and 1 for X's and Y's, put the dots down, that would give us complete spatial randomness. And that's what we would see. So the first question is, what does complete spatial randomness look like? These are actual data. These are not simulations. Are any of these random? What do you guys think? No? No?
I mean, just having the comparison of the three, the one that seems the closest to random would be the Japanese maple. I mean, it seems like the redwood is spatially clumped and the cells are, I forget what the precise term is, but they're, distributed fixed distances from each other.
Yeah. So you've been looking at a lot of spatial data.
I don't know.
Because often people will look at this and think they see all kinds of pattern in here. And in fact, this when you generate, if you actually generate random maps, it turns out you see these kind of gaps, and when spatial randomness, sometimes just by chance you get big holes. Okay, and so so then the question is this really random? So there's a number of tests. I'll show you two. So there's one that's called the G function. I don't think the G stands for anything in particular. So the way that you calculate G is you pick an event at random or arbitrarily, and then you say what's the distance to the nearest other event, right? So for this point it would be that distance, for this point it would be that distance, for this point it would be that distance, and so forth. So we generate a distribution of these G's, and then so we have this distribution of distances, basically one for each point, one for each event, and then the function takes that and maps it onto a distance space. Okay, so basically it's saying G of R is a distance or a radius, and G of R is the number of these distances that are within distance R or less. Okay, so in this case, there are lots of really short distances, short R's. There's a few cases, not many, where it's that far. Okay, and so so G of R is really just the cumulative distribution function. Where's the eraser? Cumulative distribution function of those distances. So it's going to be some kind of increasing function. Right, so in that middle one we have lots of short distances. So this is R is distance, lots of short distances, and then we get to a point where actually probably almost in this sample it's like it pretty much asymptotes. Okay. Whereas those cell data, right, there are very few short distances, and so and then you get to sort of threshold distance, and you see a lot of distances like that, and you might see something like that. So it's the cumulative distribution function of nearest neighbor distances. And so if under the condition of complete spatial randomness, then we expect this function, this
function representing complete spatial random?
It comes about because if you can, it comes about from this notion that in a given area we have a Poisson distribution of occurrences. So this is essentially this is the probability of having 0 occurrences in a region of size of area pi r squared. So it's a 0 term from the Poisson distribution. Or I guess actually this is a 0 term from the Poisson distribution. Okay, and so here is here is this function calculated for these 3 distributions. The black line is the actual distribution, and the envelope. These envelopes are, I think they're based on simulations where you take the same number of points, the same average intensity, and actually put them down at random. Calculate the G function from that random field. And so depending on how you'll remember these 3 data sets have different number of points. The larger the number of points, the narrower this sort of theoretical expectation of distribution, or this is the sampling distribution under the null model of complete spatial randomness. And so what we see is the Japanese maple, their pattern is consistent with complete spatial randomness, and then the other 2 deviate in opposite directions, right? So here's what I said before, is that you have to go out to quite long distances before you start to see any pairs of neighbors that are that close together. So it's a very kind of uniform spatial distribution. In the redwoods, we have a lot of clumping, so there's an overabundance of short distances relative to complete spatial randomness. A similar idea is the F function, which instead of taking the distance, looking at distances between pairs of occurrences, it picks a point anywhere in the plane and says, what's the distance to the nearest point? Okay, so it basically says if I parachute down at random, how close am I going to be? Or how far away is the nearest tree? And then similarly, you look at this distribution now, which is basically you can map every point on the plane, say how far away is the nearest event, and then again look at the cumulative distribution function. It's not going to be a continuous function because there's an infinite number of points you can measure it from, and again under complete spatial randomness, the expected value has this same form, right? It's still this notion of here we have the probability of 0 events in an area of pi r squared, and so this is the probability of having being at least r squared of r away from the nearest event. always gonna be that far. The near the neighbor distance is always gonna be that far. With the F function, and in contrast that with the random case where there are gonna be a lot more short distances. In the F function, you know, I'm sampling everywhere, including in the white space. So I'm gonna have distances, lots of distances up to, you know, the half of the distance between points. Whereas in contrast, in the random case, there's gonna be more observations, more places where the distance, the nearest event is actually longer.
So it sort of gets flipped.
So it gets flipped. And what this is actually plotting, it's not, so this is not actually plotting the g function that I've drawn there. It's not plotting g, this is not g versus distance. This is the empirical g versus the predicted g under complete spatial randomness, which is that 1 minus e to the 1 minus e to the minus lambda pi r squared. So this theo is sort of the theoretical.
And in the F function, do you choose every point in the space, including the points that have observations on them?
Yes, I mean, I think in practice you do a numerical discretization of the space, but yeah, you don't discriminate against points. Okay, so these are just two different ways of looking at, you know, spatial, or, you know, asking whether something is, again, the notion is, you know, is the pattern consistent with complete spatial randomness? And you could think of this as being, you know, saying for Japanese maple, we can't reject the null hypothesis of CSR.
Are the envelopes confidence intervals?
Yeah, so the envelopes are based on, you know, you run 1,000 simulations and then look at the middle 95% of them. Okay. So, you know, the complete spatial randomness, I mean, there's a number of ways you could generate complete spatial randomness, but the one that's sort of most easiest to think about and that is usually used in theory is called the homogeneous Poisson process, which is what we've really already been talking about. That the number of events in some area A is just lambda times the area. There's an expected number of events. So within the whole region, the number of events is lambda times A. So whatever lambda is, if lambda is 10 and you've got a unit area, that means you're putting 10 points in that area. And then they're uniformly distributed, so there's no pattern either vertically or horizontally. So this homogeneous Poisson process is stationary and isotropic. The easiest way to violate complete spatial randomness is to say that lambda varies in space. And you can do that and have the inhomogeneous Poisson process, which is, you know, the total number of events is still the average value of lambda times A, but there's going to be more points in the areas where lambda is large and fewer points in the area where large lambda is small. And there are procedures for, there are algorithms for simulating these, say, inhomogeneous point process. So, and the flip side, of course, is you can estimate the intensity. You know, if you have a homogeneous spatial point process, right, your estimate of the intensity function is just how do you fit this? Okay, right, what is it, so we can write this equation down, but how do we get the coefficients? So it's solved using maximum likelihood, and the likelihood function is given your data, your x's and y's, and a guess at the parameter values, you can predict the value of lambda at every location. You calculate those values where you observe the data, and then you have the constant of integration, which this basically gives you the average predicted lambda across the whole region. And then this formula gives you the likelihood, and then we simply adjust the parameter estimates until we get the maximum likelihood. And so this, so this could be done right here. It's been done where the independent variables are just spatial locations, but it also could be if we had maps of other variables, we could include those in the model as well. Okay, so if we had maps of elevation or soils or something like that, we could just as well include those in the model. So these two, both the homogeneous Poisson process and the inhomogeneous Poisson process, assume independence among events, right? So it says that, given that there's some spatial fields or some spatial variation in lambda, once you've got that, the fact that there's a point here, or the probability of getting a point here, is independent of whether there's already a point here. Okay, so there's spatial dependence, but there's not dependence between, there's spatial dependence on the background field, on the intensity function, but there's no dependence between the individual events. So often that's going to be violated, right? If we think about whatever the process is that's generating, in reality, what's generating these events. So, for example, in trees, if seeds don't disperse very far, then the parent tree is going to tend to be surrounded by its offspring, and so you'll have, the location of a young tree is dependent on the location of older trees. This would tend to create a clustering pattern that was unrelated to whatever the extrinsic intensity function is. And then in contrast, if there's say competition between individuals or maintaining territories, then you'll see a more even spacing than would be expected at random. Okay, so if you actually tried to fit and there's an example of this in the reading, if you actually tried to fit a spatial, an inhomogeneous Poisson process here that uses a sort of a local distance weighted type thing, then you actually you predict that there's all kinds of hills and valleys in the intensity function here. More likely, this is just clustering due to the non-independence of events. But the statistics won't tell you which of those is the right interpretation. Maybe there really are hills and valleys here, and we don't know just from looking at these data. So that's where understanding the process that underlies the generation of these points and whatever other potential explanatory variables are out there become key. So one way to generate a stochastic process that represents that notion of trees having offspring around them, you start off by creating a set of, quote, parent events. So you have a Poisson process with intensity rho, which is less than lambda. So you've got a bunch of parents, and then each parent produces a random number of offspring, which is drawn from some probability distribution P sub S, which is the same for all individuals, so there's no, it's homogeneous across individuals. And then those offspring are distributed at random around the parent according to some bivariate distribution. You know, it could be a bivariate normal. It doesn't have to be radially symmetrical. It could be you know, it could be elliptical. It could be biased in a particular direction to represent you know, wind or something like that. But again, it's this probability distribution function H is the same for all the parents. Okay, and so this then is a way of generating a random clumped pattern. Okay, where the degree of clumpiness has to do in part with what the average number of offspring is and how narrow the distribution of offspring is. And there are algorithms for generating hyperdispersed. So the opposite of clumping is dispersion. So a hyperdispersed distribution is like the cells that are very evenly distributed, and there are algorithms for doing that as well. So yeah, so contagion, or another way to talk about it is contagion, which is clumping, and inhibition, which is the presence of one event inhibits other events from occurring here. And one of the sort of classic books on this is out of print. It's by someone named, statistician named Diggle. And he has other more recent publications, but this is kind of this is a 1983 book that was statistical analysis of spatial point processes, and it just sort of pulls together, you know, a lot of the theory and sort of this is 83. This is pre-computational statistics for the most part. So it's got a lot of the theory and the algorithms that you can use, you know, with a slow computer or a calculator. But it goes through in quite some detail all these different kinds of patterns and how you can generate them, and what stochastic processes can be used to generate them. So questions about this? It's been kind of a whirlwind tour. And the first time I read this, it was in a graduate seminar. We spent the whole quarter reading this book. Okay, so now we're going to go on to a particular application which, it's an ecological or conservation biology application, although you can imagine other uses of it as well. So the idea of a species distribution model is that we have a bunch of observations. So here's geographic space. These pluses are places that we have observed the species. And there's two things that we want to predict. There's lots of things we might want to predict, but two that we're most commonly interested in is, first of all, given this set of observations, where do we think the full range of the species might be? Okay, if we haven't searched everywhere, you know, we could say, well, where else would be a good place to look for this species, or where would be good places to set aside reserves where the species might live, and so you know the gray, this gray area represents, we might imagine, that this is where the species actually lives, right? And so there's this area A that we haven't explored, but it's out there. And then we could say, well, here's where it actually lives, but typically species don't live everywhere that is suitable for them, or many species don't. And so we could say, what's the potential distribution? And that's the larger white areas. So this is the representation in geographic space, these three disjunct areas. And the notion is that if we take each of these locations and map them on some environment space, so here we have two environment variables, E1 and E2, that all of the potential distribution is sort of in some contiguous part of the environment space. The actual distribution is a subset of that, perhaps. Perhaps the species is not using the hottest parts of its range, is not currently in places that are within its physiological tolerance. And then the observations we have are a subset again of that. And so typically what the general notion is we have a bunch of observations in geographic space, these pluses. We collect environmental data, come over here to the environment space, plot these, plot our observations in environment space, use some sort of model to extrapolate, to basically identify what what part of the environment space the species inhabits, and then project that back in geographic space, right? So that we might assume that sort of anywhere in this region we're quite sure is a suitable environment space, right? We're surrounded in environment space by observations. So look back on the map and say where are all the places where the environment looks like this, and some of them might be up here. That's the basic idea of species distribution models. The interesting thing is, and we'll try to get back to this at the end, in practice, we might also expect that there might be some spatial dependence, right? There might be some spatial the location of the species. Well, there's two kinds of spatial dependence. There might be, spatial dependence that arises because the species tends to aggregate. But there's also could be spatial dependence in the sense that there are other environmental variables that we haven't measured that are spatially autocorrelated, just as there were in geostatistics. That latter case can be accounted for in many of these techniques that are used for species regression, species distribution modeling, but in the species distribution modeling field, that's never been done, or rarely been done. Certainly not described in the reviews that I've been reading through. So that's an interesting opportunity there. Yeah.
Maybe you're going to explain this more, but I think I don't quite understand the potential distribution. Is that, it seems like a lot of that would be just because we don't 100% understand what factors are important for the species. So wouldn't that area be large if you were thinking temperature is the only thing that matters for these species, but as you add more factors, you understand, no, it's not just temperature, it's also these three other factors that your potential distribution is going to shrink as you get a better understanding of what factors are important to them?
That could be. So it could be that this distinction, the notion that what you're saying is that basically a species is going to be everywhere it can be, and that we just don't understand enough about what the factors are controlling it. But some of the factors that are controlling where it can be may not be environmental. They may be, maybe there's a mountain range that runs like this. Okay, so there's just a barrier of dispersal, but the habitat over here, if it could cross that mountain range, is perfectly suitable. And so, in that case, in terms of where it's going to get to by itself, these areas are irrelevant. But if we're thinking about doing introductions or worrying about invasions, right, those are very relevant places to look at.
So your assumption in this potential distribution is that you've understood everything that there is to understand about this species, and there's no good reason you can account for why it's not there, other than it just hasn't made it there yet.
Right. Yeah. And so this potential distribution is often modeled, I mean, there's some examples where they're looking at invasive species and asking what other geographic regions are at risk from this species, right? Or if we're looking at future climate, and so we sort of shift, in this case, taking the same environment space and shifting it into geographic space, where is that going to be? So this is just a long list of applications. So you can, there's been sort of some applications where they use species distribution models to ask, well, where should we go look for more occurrences? Talked about climate change and invasion. So, helping with reserve selection, so identifying this as even if we don't go look for the species there, this might be a good potential reserve site. And, where to do reintroductions, right? So identifying good potential sites for reintroductions and so forth. And there are lots and lots of models that have been developed to do this. They tend to have it's a bit like the decision theory stuff. There's all these funny names that have acronyms and sort of written in all caps all the time. They don't really mean much. The main thing to look at, focus on here, is that behind all of these funny names, there's a bunch of different analytical approaches that are being used, and there's some differences in the kind of data that are used. Okay? So there are some that only require the locations where the species was seen. Okay? There are others that require presences and absences. So we know that species are found in these places and are not found in those places. And if we don't have, so we'll come back. And there's others that look at the back, so the presences and the background, which is the whole field of the environmental space. Okay, regardless of whether the species is there or not. So we'll talk about that, those distinctions. So the presence-only methods, okay. What they do is they look at the environment space of where the species was seen, and characterize that environment, and then when go back to the map and explore other locations on the map based on how similar they are to the environment at the species locations. Okay, so for example, right shifts.
Looks familiar?
Yeah. So who was this? Is this Lee Hanna's course? Anybody taking Lee's course? So if we have our two environment variables, right, and we have our observations of the species locations, and they're sort of span a, have a distribution in this space. There's a flavor individual right there. basically it says, okay, the most, you know, one of the simplest ways, which is the bioclimb is the model, and it's often called the climate envelope model. Basically just says, well, for simplicity, let's just look at E1 for a minute, and we say, well, what's the most typical value of E1 for the species? Well, it's going to be the median. Okay, so the median in E1 is about here, right? And you know, we might say that you know, the kind of good range is you know, from the 25th percentile to the 75th percentile, so the middle 50% of the distribution, right? And so this would score as a high score, and then you could say, well, between this middle 50% and out to the middle 80%, right? So which would be from the 10th percentile to the 90th percentile, right? You just sort of build up these percentiles around this empirical distribution of environment where the species was found, and you know, score it more highly the closer you are to the median. And then you can do that for you know, for all the variables. The simplest way is simply to say, yeah, and suppose we want to say that anything that's within the, you know, the middle 85%, right, is good habitat, right? So one of the simplest ways is simply to take, you know, the 85th percentiles with the middle 85 on each of these variables, and right, and say that anything in this part of environment space is good. A more sophisticated way might be to use, you know, you can kind of construct bivariate, or in the case of more environmental variables, multivariate density functions, right, to actually get contours that better represent these data points, and then use this as the you know, anything within this contour as representing good environment.
Wouldn't you, I mean, a lot of times when people end up doing like a PCA first to determine the most important ones, or, I mean, how do you know when you're measuring everything if, oh, actually, temperature doesn't matter at all?
Right. Well, it's how would you know temperature doesn't matter at all? Yeah. So the process of selecting variables is. I mean, have you actually done this?
No, I've just, you know, read
Yeah.
papers that people, I mean, it seems kind of overwhelming to
Yeah.
find all the, you know, the environmental variables that matter the most. Seems like it would be a challenging.
Right. So yeah. So part of the question is, yeah, how do you identify which environmental variables? One approach is just to take them all and throw them in. Everything you can get measurements of. You can try to use some biological knowledge to filter that a bit. Sometimes, or often, it seems that you can actually get better predictions by creating some aggregate variables that better represent what really matters, and that could be, you know, instead of minimum January temperature, it might be, you know, cumulative degree days below freezing or something like that. Sometimes the sort of generalized climate indices, like the NAO index or the ENSO index, do better than locally measured environmental variables, because what they get at, for example, the NAO index in the North Atlantic, for islands in the North Atlantic, the NAO index sort of gives you it turns out to be correlated with certain patterns of storms in certain seasons that have particularly strong effects on in terms of statistically how you decide, in all of these methods, in all of these approaches to species distribution modeling, there's a attempt to do validation. And typically, you do the validation, if you're not going to go out and collect new data, you would do cross-validation. Probably not leave one out cross-validation, just because these methods tend to be more time consuming. But five-fold cross-validation, 10-fold cross-validation, and then try to identify the models, both the models and the overall techniques that seem to give the most reliable results. So one thing about this approach is that it doesn't take into account the availability of these environmental variables, right? It could be that the reason that there are so few observations of the species with this really high value of E2 is that in the landscape there's only a couple of places that have high values of E2. Okay, so we actually don't know anything about whether or not this is just a random sample of what's available out there. And there's, the other, so BioClimb actually, from what I've read, is kind of, it's not a recommended technique. It performs poorly. It's only still out there because it's easy to explain. But a presence-only method that is still used is called domain, and that uses something called the Gower distance, which is quite complicated to explain. But basically, what it does is you take. So if we go back here, get rid of these contours. Okay, and so we take a point in environment space, and we say, what's the nearest observation in the E2 direction, right? So that's that distance. What's the nearest observation in? Well, I take that back. So it's not that distance. It's it's that distance. Okay. What's the nearest observation in the E1 direction? That distance. Okay. And then so you calculate those for at any given arbitrary point in environment space. You calculate those distances. They're scaled appropriately, and then you take the mean of those distances across all the environmental variables, and that's called the Gower distance. Okay, so it's a distance metric in the environment space that says how far away am I from the nearest place where the nearest part of the environment where the species is observed. And that seems to work better than simply putting empirical confidence intervals around the observations. If we have absences as well as presences, right? We have a bunch of places on the landscape that have environmental variables associated with them, and we record either presence or absence. We can do a logistic regression. Okay, and so it can be a parametric logistic regression, which just says, well, let me put this slide up in a second. But before we get there, suppose, we said that in many cases, all we have are the presence data. So a common approach is to generate pseudo-absences, which is to go to pick places on the landscape at random simply say, and often, yeah, you might buffer around the points and say, outside of a certain distance from where the presences were observed, I'll just pick points at random and I'll call them absences. And of course, there's potential error that comes up with that. So, back up again. So just to remind people, so GLM stands for Generalized Linear Model, and it just means, in contrast to the ordinary least squares model, it just says that, the left-hand side, the dependent variable is not just a variable, but some transformation of it, and the distribution is not necessarily Gaussian. So for logistic regression, it simply just says that, so if Pi is the probability of seeing a presence at location I, right, then the logit of Pi, which is just the log of Pi over 1 minus Pi, so it's the log odds, basically, is some linear function of the explanatory variables, right? So it's beta naught plus beta 1 times environment variable 1 at I plus beta 2 times environment variable 2 at location I, and so forth. So it's just, standard logistic regression. Here's where I mentioned that you can include a spatial term. So this part is just a parametric equation, and then g of x, g is just some smooth function of where x is space. So there's some unknown smoothly varying function across the landscape that represents all the spatially correlated residual variation that's not captured by the environment variables that you've measured. And typically this is fit by, for example, some kind of non-parametric smooth function like a spline, and you just let this, you have to sort of pick some parameters that tell you how much that function is allowed to wiggle across space. But then, then it just it finds a particular pattern that, when combined with these predictor variables, maximizes the likelihood of this model. Who knows what a GAM is? Nobody. Who's heard of a GAM?
Related to GAMS?
Might be. I'm not sure what GAMS is. So GAM stands for Generalized Additive Model. Okay. So remember that in a generalized linear model, the linear part means linear in parameters, right? So that the parameters have to be out front, multiplying everything. In a GAM, we say that the logit of P is an intercept plus, so it's still additive, but now we're just going to say F1 of U1 plus F2 of E2, and maybe there's an F3 of U1 and E2, okay, for interaction. And these functions can be arbitrary nonlinear things that have parameters in them that can't be estimated via least squares or anything like that. So obviously this has to be done. There's no the reason why linear in parameters matters is because it allows access to a whole bunch of computational tricks that make the fitting go really fast and that guarantee that you get the best fit. Here we're basically doing nonlinear minimization, which is, you know, a somewhat fraught process. But what's nice about this in practice, when people say YAM, what they really mean for these Fs is that rather than specifying a functional form, they'll typically specify a spline. So a spline just is a function. I mean, it is a function, but you basically say that let's see, I'll explain splines. Short amount of time. A spline, a one-dimensional spline, in one dimension, a spline, you know, so say we've got a bunch of data, right? A spline, you know, would be something that we allow freedom to fit whatever shape the data seem to give us. And it can be a smooth spline like that. It can, if we allow it, it can try to fit the wiggles. Right? If we give it enough degrees of freedom, it can actually become an interpolator and wiggle like mad. Okay, so we have to tell it, you know, if we give it just 1 degree of